6 days from now, if the schedule holds, a Falcon Heavy will rise from Florida, carrying a telescope that could change the way we see almost everything in the universe. It is not replacing Hubble. It is not replacing James Webb. It is doing something neither of them was designed to do. Imagine taking a Hubble image just as sharp, just as deep, and suddenly making its view at least 100 times wider. Instead of studying one small cosmic neighborhood, you can begin mapping the whole city. NASA calls it the Nancy Grace Roman Space Telescope. And after years of construction and testing, mission managers have completed the flight readiness review. Roman is now targeting launch no earlier than August 30. If it works, it could find thousands of new planets, map invisible dark matter, test whether our theory of gravity is incomplete, and reveal violent events that other telescopes simply were not looking at the right moment to catch. But Roman's most important discovery may be something nobody has predicted. For more than 3 decades, Hubble has shown us the universe in extraordinary detail. James Webb has pushed even deeper into infrared light, studying the earliest galaxies and the atmospheres of distant worlds. But both telescopes have a limitation. Their view is narrow. That is not a flaw. It is like using a powerful telephoto lens. You can see a tiny patch of sky with astonishing detail, but surveying an enormous region takes many separate observations. Roman changes that equation. Its primary mirror is 2.4 meters wide, the same size as Hubble's. Its images will have comparable sharpness in near-infrared light, but Roman's wide-field instrument sees a patch of sky at least 100 times larger in a single pointing. NASA says it can survey the sky up to 1,000 times faster than Hubble while maintaining similar sensitivity and infrared resolution. In its first 5 years, Roman is expected to image more than 50 times as much sky as Hubble, covered in 30 years. That scale is the entire point. Astronomy has often advanced by studying a few remarkable objects in extreme detail. Roman will add another method, observing millions or even billions of objects consistently, then looking for patterns, outliers, and changes. It is the difference between examining a few trees and finally seeing the shape of the forest. Roman's biggest target is not a planet or a galaxy. It is a mystery built into the expansion of space itself. In the late 1990 seconds, astronomers discovered that the universe is not merely expanding. Its expansion is accelerating. Something appears to be pushing the cosmos apart faster and faster. We call that unknown influence dark energy, but the name is not an explanation. One possibility is that dark energy is a property of empty space. Another is that it changes over cosmic time. A more radical possibility is that Einstein's general theory of relativity, one of the most successful theories ever created, begins to break down across the largest distances in the universe. Roman will test these ideas in several independent ways. It will find tens of thousands of exploding stars called Type Ia supernovae. Because their brightness can be used to estimate distance, they act like mile markers across cosmic history. Roman will compare how far away they are with how quickly their galaxies are moving from us. It will also map the three-dimensional positions of millions of galaxies. Tiny patterns in that cosmic distribution preserve information about how the universe expanded and how large structures grew. If all of these measurements point to the same answer, our current model becomes stronger. If they disagree, the disagreement could be the discovery. Dark energy affects how the universe expands. Dark matter affects how galaxies and clusters are built. We cannot see dark matter directly because it does not appear to emit, absorb, or reflect light. But we can observe its gravity. Mass bends spacetime, and bent spacetime changes the path of light. When light from a distant galaxy passes through a large concentration of matter, the galaxy's image becomes slightly stretched or distorted. This effect is called gravitational lensing. One distorted galaxy tells us very little. Hundreds of millions of galaxies can reveal a map. Roman will measure the tiny lensing distortions across enormous regions of sky. From those measurements, scientists can reconstruct where matter, including invisible dark matter, is concentrated. That map can then be compared with the history of cosmic expansion. And this is where the mission becomes more than a better camera. If gravity is building structure at one rate, while the universe is expanding at another, our standard model may be missing something fundamental. Roman could show us whether dark energy is truly an unknown form of energy, or whether gravity itself needs to be rewritten on cosmic scales. Roman's second great survey will stare toward the crowded center of the Milky Way, monitoring around 100 million stars for hundreds of days. It will not be searching mainly for the regular dimming that happens when a planet crosses in front of a star. Instead, it will use a stranger consequence of gravity, microlensing. When a foreground star passes almost perfectly in front of a more distant star, The foreground star's gravity bends and magnifies the background light. If a planet orbits the foreground star, it can create a second, smaller flash in the signal. These alignments are rare. Some of the most important changes last only hours. But Roman's wide view and precise monitoring are designed for exactly this problem. NASA expects the microlensing survey to find about 2,500 planets. It should be sensitive to worlds smaller than Mars, and to planets orbiting far from their stars. The cold, distant population that many other surveys struggle to detect. Roman may also discover free-floating planets, worlds that were thrown out of their systems and now drift through the galaxy without a sun. The result will not just be a list of unusual planets. It will be a statistical census that helps answer a deeper question. What kinds of planetary systems does nature usually create? Is our solar system common? Are Earth-sized planets at wide distances rare? How many lonely worlds are moving through interstellar darkness? Roman could give us the first reliable population-level answer. Roman also carries a second instrument, a Coronagraph technology demonstration. Seeing an exoplanet directly is extremely difficult. A star can be billions of times brighter than the planet beside it. It is like trying to photograph a firefly next to a lighthouse, from thousands of kilometers away. A coronagraph blocks the star's light inside the telescope, allowing much fainter objects nearby to become visible. Roman's coronagraph is not the mission's main survey instrument, and it is officially a technology demonstration. That distinction matters. NASA is testing advanced systems that control and suppress unwanted starlight with extraordinary precision. If it performs as intended, it will help prepare the technology needed for future observatories that could directly image smaller, more Earth-like worlds. Roman is therefore searching for planets in two very different ways, discovering thousands through gravity, while testing how future telescopes may photograph worlds directly. A wide view becomes even more powerful when the telescope returns to the same region again and again. Roman can create cosmic time lapses, repeated images of enormous star fields and galaxy fields. Anything that changes can stand out. Stars can flare, supernovae can ignite, black holes can tear stars apart, asteroids can move through the foreground, distant objects can brighten because of gravitational lensing. Some events may last months, others may last only hours. This gives Roman a discovery mode that is difficult to plan in advance. Scientists do not need to know exactly where an event will occur. They can watch a large enough region with enough precision and let the universe reveal what changed. NASA expects Roman to observe light from as many as 1 billion galaxies over its lifetime. In a dataset that large, even extremely rare events may appear more than once. That matters because one mysterious object can be dismissed as an accident or a measurement problem. A population of similar objects becomes a new category of science. It is tempting to describe every new telescope as a replacement for the last one. That is not how modern astronomy works. James Webb is exceptionally powerful at taking deep, detailed observations of selected targets, especially in infrared light. Roman is optimized for wide, systematic surveys. Roman will find enormous numbers of interesting objects. Webb, Hubble, and ground-based observatories can then study the most unusual ones in greater detail. Roman is the scout. Webb is one of the investigators. The combination is more powerful than either mission alone. A strange early galaxy found in a Roman survey could become a Webb spectroscopy target. A planet detected through Roman microlensing could become part of a broader population study. A transient event could trigger observations across Earth and space. The new era is not defined by one telescope. It is defined by telescopes working as a system. Roman is scheduled to launch on a SpaceX Falcon Heavy from Launch Complex 39A at NASA's Kennedy Space Center in Florida. NASA and SpaceX completed the flight readiness review on August 21 and certified the mission to begin final launch preparations. The target is no earlier than 7:26 a.m. Eastern Daylight Time on August 30, but a launch date is always a target, not a promise. Weather, technical checks, or range conditions can change the schedule. After launch, Roman will travel to a quasi-halo orbit around the second sun Earth-Lagrange point, known as L2. That is roughly 1.5 million kilometers from Earth, in the same broad region used by the James Webb Space Telescope. Its primary mission is planned for 5 years, and the observatory is designed to support a 5-year extension. Roman's data will have no proprietary period after processing and delivery to the archive, meaning researchers around the world can begin working with it. That open archive could become one of the mission's greatest strengths. The scientists who discover Roman's most surprising object may not be members of the team that planned the original observation. Roman's power is easy to summarize with one number: a field of view at least 100 times larger than Hubble's. But the number is not the real story. The real story is what happens when astronomy moves from isolated examples to enormous populations. One strange galaxy can challenge a model. 1 million galaxies can test it. One distant planet can inspire us. Thousands of planets can show whether our own system is normal. One warped image can reveal a gravitational lens. Hundreds of millions can map invisible matter across the universe. And one unexpected flash, hiding inside years of repeated observations, could become the first example of something we have never seen before. Hubble taught us how beautiful the universe is. Webb is showing us how early its structures formed. Roman is about to show us how all of those structures fit together on the largest scales. If the launch succeeds, the first great surprise may not be one of the discoveries Roman was built to make. It may be the discovery nobody knew to search for. End screen line. If you want to follow up the moment Roman launches, subscribe to Space Origins and watch our video on the 10 ways the universe could end next.